Okay, right. Okay. All right. Good evening. Good evening, all. First, can you confirm whether I'm clearly audible and visible? I'll check from my end also. What about the audio and video? Fine, right? Fine, okay, fine. Right. Then we'll start. Right. So today we are going to step into the next part in electronics. That is unipolar transistors. Since we have completed all the applications, everything about bipolar transistors last week. Right now, today we are starting unipolar transistor, the next part in transistors. Right. So we are starting the unipolar transistor, and the stance we are now is like just 5 weeks from the exam. Right, just 5 weeks from the exam. Time flies, right? And we are just 5 weeks from the exam. Exactly 5 weeks and 1 day remaining. 5 weeks and 1 more day remaining from the exam, right? So time flies by, time flies. Right, we have to manage everything, right? So I know these days kind of a workload is there, right? That's normal, that's completely normal when it comes to these days of an A-level student, right? That is completely normal, right? So managing three subjects is the thing here, and that should be your main focus these days. That's it. Managing all three subjects is your main focus. That's it. There's nothing other than that these days, and don't do anything other than that, right? Because if you read, then you will have to face the consequences very soon. That's the thing, right? And about tomorrow, right? As I have shared already, capacitors seminar is also happening, right? So I'll cover the full lesson capacitors tomorrow, right? We'll be starting at 7. We'll be starting at 7. And the week after this week, 12th, right? Yeah. Tomorrow is 5th, no? Then on 12th, we'll be having the electricity practical seminar. And then we are going to line up everything that day, right? In terms of the practicals also. Right. So those are the things coming up. And in the theory class Thursday, since the syllabus is over, right, we'll be spending our time with questions, right? And other than that, some more question discussions will also be coming up, right? Other than that, some other question discussions also coming up during the month. So stay connected, keep in touch, and always engage with the things. That's the thing, right? Engage with these things and spend your time effectively and productively, right? So that's the thing these days, right? And yeah, right. There you go, mate. And again, I uploaded the each practical short video wise to the channel also, right? Seminar videos are the you know, because they are in seminar videos, right? Anyway, since they are like 7 hours, 8 hours long, right? So even though they are long, it was chaptered, but yet I decided to trim more videos into the practicals, each practical, and publish again, and that is published already, and the rest will be also publishing in the next days, right? Then from there also you can find all the experiments if a requirement came, right? If a requirement came. Okay, then we'll start. As the heading lined out, unipolar transistors. Unipolar transistors. Unipolar Unipolar transistors. Unipolar transistors. Unipolar transistors. Right. So previously we were discussing about bipolar transistors. Right. Bi means two. Right. Bi means two. In bipolar transistors, what we had was, right, we had two types of carriers which contribute the operation of transistor. Right. We had two types of carriers which contributes for the operation of transistor. Right. They were namely majority carriers and minority carriers. Right. If we take a transistor like NPN, majority carrier was N electrons, minority carrier was protons, holes. Right. So that's why we call them bipolar transistors. Right. There are two reasons actually. First one is there are two carriers contributing, and the second reason is there are two PN junctions. Right. There are two carriers contributing, and there are two PN junctions. So they are called bipolar transistors. By here they are unipolar. In unipolar, they have only one type of carrier, either NOP, either electrons or holes, and there is only one PN junction. Right. Only one PN junction and one type of carrier. Right. So that's why they are called unipolar transistors. Right. So first we'll see the differences between unipolar and bipolar. Then easily we can develop the lesson on that. Right. Under that, write down differences between, as a subheading, write down differences between differences between differences between differences between differences between bipolar and unipolar transistors. Differences between bipolar and unipolar transistors. We'll do this on a table. We'll do this on a table. Have a table. Have a table like this, and take this side for bipolar and this for unipolar. Fine. We'll be writing these facts one by one. We'll be writing these facts one by one. Right? Take it down. Take it down. Right, bipolar energy. Right, right down. First on. Both electrons and holes. First point, huh? Both electrons and holes. Both electrons and holes have a shelf life. This right. Okay. Right. This side, bipolar side, right down bipolar. Both electrons and holes. Both electrons and holes act as carriers. Act as carriers. Both electrons and holes act as carriers. Both electrons and holes act as carriers. Both electrons and holes. Right? In unipolar side, write down unipolar side. Either electrons or holes. Either electrons or holes. Right? This shows electrons and holes. This is electrons and holes. And this side, either electrons or holes. Either electrons or holes act as carriers. 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 Right? Then second point on the bipolar side. Second point on the bipolar side. There are two PN junctions. 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 Sound is little bit different than other days. Is it? Is it same for all of you? Is it same for all of you? Can someone else confirm? Is there any difference in the sound? Yes. No. Yes, no, I don't know. Different means, what do you mean? Is it not clear or what's it? I mean, what do you mean by being different? Clear නැත්නම් තව වෙන මොකක් කරේ අවුලක්ද තියෙන්නේ? Okay. What do you mean by different? Clear? Too loud. Too loud case තියෙන්නේ. No. The thing is this. I think I switched on you mic, right? So because of that, sometimes there can be a difference as well because of the new mic, right? That's a new one, no? That's a new one. I used this yesterday also, but yesterday in the yesterday class, 27 plus, they didn't say anything like that. Too loud. Too loud, and just lower it down, right? I think I haven't increased the volume. මේ mic volume levels තියෙනවා මම ඒක average එක moderate level එක තියලා තියෙන්නේ. ඒක අවුල නැහැ. You can adjust the volume by your side, no? Okay, clear නිකන් අවුල නැහැ. Right, okay. Then bipolar side, there are two PN junctions. There are two PN junctions. There are two PN junctions. Right? Then unipolar side, there's only one PN junction. There's only one PN junction. There's only one PN junction. There's only one PN junction in the border side. Right, Mark, check the I also check the video and audio. I think there's no issue. I think there's no issue if the issue is loudness. Loud down. Right. This side there's only one PN junction. Unipolar, there's only one PN junction. Right. Then in bipolar side, listen. Now we know we had two PN junctions, and about the operation of these two PN junctions, we had something special. One PN junction out of these two should be forward biased, and the other PN junction from these two should be reverse biased for the proper functioning. Right? In a bipolar transistor, one PN junction from these two is always forward biased, and the other is always reverse biased. Right? And here in a unipolar transistor, that single PN junction is always reverse biased. Right? In bipolar side, write down. One PN junction is forward biased. Bipolar side. One PN junction is forward biased. One PN junction is forward biased. One PN junction is forward biased. And the other is reverse biased. And the other is reverse biased. One PN junction is forward biased and the other is reverse biased. Right? Then unipolar side. PN junction is always reverse biased. Unipolar side, PN junction is always reverse biased. PN junction is always reverse biased. PN junction is always reverse biased. Right. In bipolar transistors, we know, right? We have two types as NPN, PNP. NPN and PNP. Right? In NPOL also, we have two types as N channel and P channel. Right? Bipolar side write down. There are two types as NPN and PNP. There are two types. There are two types as NPN and PNP. 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 Right? The unipolar side, there are two types. There are two types as N channel and P channel. This is how it's written: N channel and P channel. N channel and P channel. There are two types as N channel and P channel. Two types as N channel, P channel. Two types as N channel and P channel. N channel and P channel. Right? Then on the bipolar side, a current control device. A current control. Right? A current control device. One example is the general equation of a bipolar transistor was I equals IB plus IC. Right? We did everything using currents. Right? We did everything using currents. Right? Doing everything using currents means, right? Doing everything using currents means the regions of transistor is determined by the current. Controlling is totally done by the current. So that is called current control device. When it comes to unipolar, that is not a current control device. That is a voltage control device. We will see in the coming parts. Right? The main equation, general equation of this transistor is also based on a voltage. Right? So that is called a voltage control device. Write down on the unipolar side, a voltage control device. 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 A voltage control device, right? Now I mic check करें, problem नहीं है. I again check the from the mic actually the sound. I check the sound again. I think there's no issue. Right, but again, if anything, just let me know. Right, as the next heading, write down. Next heading. Physical appearance. Right, physical appearance. Physical appearance. Physical appearance. Physical appearance of a junction field effect transistor. Physical appearance of a junction field effect transistor. Junction field effect transistor. Physical appearance of a junction field effect transistor. Physical appearance of a junction field effect transistor. Right? So we usually call this FETs. FET, field effect transistor, FET. Right? We usually call it FETs. Right? FETs. Right, listen. So sometimes you might have seen this in circuits, right? Sometimes you might have seen in the circuits, right? It is like this. Physically, it is like this. Physically, it is like this. Has three legs, has our bipolar transistors, has three legs, has our bipolar transistors, and physically, this is how it looks like. Right? And this is also a conductor plate. Right? This is also a conductor plate. That is basically a terminal. Right? We'll see what the purpose of this terminal. Right? This is also a terminal. Right? And that terminal is exactly the gate terminal here. Gate means that's the center terminal here. Right? This is a physical appearance. Right? And as we had, listen, now I'm always comparing this with the bipolar transistor because there are many comparative things. There are many comparative things with the bipolar transistor. When we see all these comparisons, when you know these comparisons properly, right? Easily you can grab these things in the unipolar transistor very easily, right? When we check with the bipolar transistor, right? So in bipolar we had three terminals as base, emitter and collector, base, emitter and collector. Instead of base, here we have something called gate. Instead of base, here we have gate, right? Instead of emitter, we have source, and for collector, we have something called drain, right? There are three terminals like this, three terminals like this, right? This is the physical appearance. This is the physical appearance. Take out. Take down physical appearance. Right? Then okay, next somebody. Structure of structure of structure of structure of a FET. Structure of a FET. Structure of a FET. A FET FET. Structure of a FET. Structure of a FET. Right. Listen. This is structure. Structure means now inside the FET, if we deassemble, if we detach the FET, this is what we see. Right? So if you deassemble, detach the FET, this is what we see. Right? Listen, huh? I'm going to go. Right. In these sites, one type of semiconductor is here, right? So this is P, and the other semiconductor is here. Say this one is N, and there are three terminals like this, right? There are three terminals like this, There are three terminals, right? So namely gate, drain, and the source, like this, right? Now it is like this. Now when I draw the structure, sometimes you might be thinking that this is an N-type semiconductor, and this is a P-type. Then between N and P, there's one PN junction, and this is also P. Between P and N, there's another PN junction. No, that's not the case. That is not how it is. It is like this. See over here. It is like this. Now, if this is the N-type, if this is the N-type, right? This P-type is wrapped around this, like this. If this is the N-type, right? See, if this is the N-type, the P1 is wrapped around this like this. P is wrapped around this like this, right? P is wrapped around this one. P-type is wrapped around this one. Then this is the N-type, and this is the P-type. P-type is wrapped around this, right? So what you are seeing is this wrap from both sides, same wrap from both sides. Got it? I have something a little smaller. Yeah, see, something like this. This is what you see. Right? This one is N-type. And this is P. P is wrapped around this. Then how many PN junctions? Only one. Because one N and one P. Listen, one N and one P. Then only one PN junction. But when you take a side elevation like this, you'll see P at both sides, but there's only one PN because that is wrapped around this. Only one PN, right? Okay, then this is called, listen, this is called the N channel. This is how the channel is labeled. The semiconductor type of the body is always goes as the name of the channel, right? If the body is N, this is N channel. If the body is P, that is P channel, right? Main body is the type of the FET, right? Then this is N channel. You can take down now. This is N channel. This is N channel. Now, if I draw P channel, it is like this. Take down, take down. If you draw P channel, it is like this, right? For P channel, let me draw front elevation. Right? If you take a front elevation like this, gate, drain, source, right? And say this is P now, and this is N. So there is a P channel. Right? That's how N channel and P channel is identified. The type of the body is the channel. Type of the body is the channel. Take out. Okay, right? Right? Keep them in mind. Type of the body is the type of the channel. Type of the body is the type of the channel. Type of the body is the type of the channel. Right. Then let's move on. Let's move on. Next heading. Operation of a field effect transistor. Right now. Operation of a field effect transistor. Operation of a FET. Operation of a field effect transistor. 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 Right. Now, about operation also, almost everything is very comparative, right? Since that is comparative, again, I'll be doing this as a comparison with bipolar transistors when we are doing the unipolar transistor, right? Then have a table, right? We'll do everything on this, right? Have a table, and this side, take it as bipolar, right? And this side as unipolar. Right, listen now. Starting from the terminals. Right, what are the terminals we had in a bipolar transistor? Base, emitter, and collector. Right, B, E, and C. Base, emitter, collector. Right. Now here also we have three. Right, we have three. Compared to these three, right? Comparative to base, here we have gate. Comparative to base, here we have gate, G. Right? Comparative to emitter, right? Here we have source, S. Comparative to collector, here we have drain, D. Right? Take out. So starting from the terminals itself, that is comparative. That is very comparative. Right? So always when you see these comparisons properly, right, it makes it very easier to understand these things. Right. Right. Listen. Listen now. Now, first, I'm going to compare this with NPN. Right. First, you have to do these things. Draw NPN here. Draw NPN transistor here. Quickly. Draw NPN transistor here. Draw NPN transistor here. Draw NPN transistor here. And identify terminals, mark currents, mark potential differences. Alright. Do it. NPN this side. Draw NPN transistor. Identify terminals. Identify terminals. Base, collector, and emitter. Mark currents. Mark currents. IV, IE, and IC. Then potential differences. VD, VC, VG, and VCB. And write down the order of potentials, the sequence of potentials and the order of currents. Order of potential and order of currents. Right, we know these things from our learnings now. Then highest potential is at C, BC, BB, BE, and the highest current is at emitter, IE, IC, IV. Right? And write the name here NPN. Write the name of this one here NPN. Name is NPN. NPN. Right, listen. NPN. Right, listen now. Listen now. I'm going to compare this NPN with the N channel. I'm going to compare this NPN with the N channel. NPN with the N channel. Right. Now, the circuit symbol of a unipolar transistor is like this. Circuit symbol is like this. Circuit symbol is like this. Circuit symbol of a unipolar transistor is like this. Right. And as current flows into base in NPN bipolar transistor here, an inward arrow is put. An inward arrow is put. Right? An inward arrow. Very important. An inward arrow. Right? Arrow is not made N channel, P channel, maru. Then if there is an inward arrow, that is N. Right? See, now compare. Instead of base, very comparative. Instead of base, we have gate. Instead of emitter, you have source. Instead of collector, you have drain. Right? Then mark currents. When marking currents, right? Listen carefully. When marking currents, right? There are no current flows through gate terminal. There are no current flows through gate terminal. Right? Resistance of that side is very high. There are no current flows through gate terminal. We call that equation G of Vg equals 0, and there are no currents through gate. There are no currents through gate. Right? Therefore, don't mark any current in the gate. And these two current flows are very much same as this. Right? As collector current is downwards, this drain current is downwards. As the emitter current is downwards, here source current is downwards. Right? And it has potential differences. Right? Potential difference between these two is called VGS. Right? between these two VDS, between these two VDG. Alright. Now order of potentials. Listen, order of potentials. Current flows from D to S, no? Then VD is greater than Vs and Vg is always the least because this is a special thing. Because Vg equals 0, right? That is called G off. Because Vg equals 0, G off. Right? When the transistor is operated, right? We keep Vg at 0. Then about currents, there are no currents in gate, no? Then only one current comes into the transistor and one goes out. Right? Therefore, about currents, right? Is equals ID. Is equals ID about current, right? And as this is NPN, this is NJ right? Field effect transistor FET, then junction field effect transistor JFET, N-channel junction field effect transistor we call NJ right? Then short form here is as NPN here, this is called NJ and here we like the name as well. This is called method NJ this is N-channel junction field effect transistor. N-channel junction field effect transistor. Right, take down. Take down. See how comparative these are. This is a very small and easier part. Right, always compare with bipolar. That is the easiest way to learn this. Okay, right? So write the long term also, write down. Write down. If you have written, check your answers. Right? Write down the long term also. N-channel junction field effect transistor. 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 Right. Alright. So as we compared N-channel to NPN, now I'm going to compare P-channel to PNP. Right? Very easy when you compare. Right? Don't take it as two different things. No. Not the case. Not the case. Comparative. That is comparative. Unipolar transistor also has its own unique features, right? But there are very comparative features. There are very comparative features coming from bipolar learnings, right? Okay, finished. Then here, left side, right? Left side column. Then draw PNP transistor and do everything. Draw PNP and do everything. Right, draw PNP. Identify terminals, base, collector, emitter. Mark currents, IV, IE, upwards, IC, upwards. Then potential differences. Potential differences. This is VEV from here to here. This is VEC, opposite, VEC. And this is VBC. Then order of potentials. Order of potentials. Highest is VE, then VB, then VC. Then order of currents. That is same. IE, IC, IB. Right? So this is our PNP. This is our PNP. This is our PNP. Right now, I'm going to compare this PNP with the V channel. Right? Going to compare this PNP with the V channel. Very straightforward. Compare this PNP with the V channel. Compare this PNP with the V channel. Right? Compare this PNP with the V channel. Right? Same thing. Same thing. The circuit symbol is like this, and the only difference is the arrow is outwards now. The arrow is put outwards, A and B. Right? And instead of base, here we have gate. Right? Then for here drain. Right? Here source. Now currents. Now current flows are exactly same as this. Right? As IE is upwards, here ISC is upwards. Right? And ID is upwards as IC is upwards. Then potential differences. Current flows from S to D. Right? Then this potential difference is VSG. This potential difference is VSD. And this potential difference is VGD. Order of potentials. Order of potentials. Current flows from S to D. No? Then VS is greater than VD. And always VG is the least because of the same reason VG equals 0. VG equals 0, we call GO. Right? And our currents. Again, only two currents. Right? Which means current inflow equals current outflow. ISC equals ID. Same. ISC equals ID. Same. And this is our PJ FET. This is our PJ FET. Right? Right on the long term also. P channel junction field effect transistor. P channel junction field effect transistor. Right? See how easy. See how easy. P channel junction field effect transistor. P channel junction field effect transistor. Right. Take down. You can close the table after this. You can close the table after this. Right? Close the table after this. Close the table after this. Right? Finished? Right. Now close the table and write down below with the red pen. Put an asterisk mark and write down below with the red pen. Put an asterisk mark and write down below with the red pen. Write down. Write down VG equals 0. Write down VG equals 0 like this. With the red pen, write down VG equals 0. VG equals 0. VG equals 0. Within brackets G of like this. Within brackets G of like this. Within brackets G of G of G of. In JFETs, JFETs means junction field effect transistor. In JFETs, in JFET for all occasions, 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 except for all occasions except for all occasions except voltage divider, except voltage divider. Don't worry about the word voltage divider, that is coming up. Voltage divider circuits are coming up. Right. Alright. Then as the next, I need to write down applications of NJFET. Applications of NJFET. Applications of NJFET. Listen, as we had calculations only from NPN in bipolar, right? As we had in bipolar, we have calculations only from N channel in unipolar, right? So that makes it very easier again to us to study and manage this, right? අරගෙන තියෙන්නේ NPN විතරයි, මේකේ තියෙන්නේ N channel විතරයි. For calculations, for calculations, you have only NPN in bipolar and N channel in unipolar, right? So that's why we are going to check the applications, see the applications of NJFET. Right, now do this. Draw NJFET at the center of the page. Draw NJFET. Draw NJFET at the center of the page. Draw it. And do what I say. Right, draw NJFET at the center of the page. Draw NJFET at the center of the page. Identify terminals. Identify terminals. Identify terminals. Identify terminals. Right. Now extend source downwards and connect a resistor and ground it. Extend source, connect a resistor, right? Connect a resistor and ground it. Then extend gate, connect a resistor, right? Connect the resistor and bend that wire vertically downwards and ground it. Bend that wire vertically downwards, that was horizontal wire, bend it vertically downwards and ground it. And again, connect another resistor to drain and bend the wire horizontally, right? And again bend it vertically, connect a battery to satisfy that current flow. Connect a battery to satisfy that current flow, and after connecting the battery, ground the terminal. After connecting the battery, ground that terminal also. Right, now let's see what you have done. Right, check what you have done. I asked you to draw a channel NJFET. Right, NJFET. Then arrow is inside into. Right, extend. We were extending. Identify terminals, gate, drain, and source. Gate, drain, source. Extend source, connect the resistor and ground it. Extend gate, connect a resistor, right? And bend this vertically and ground it. Here, connect a resistor, bend this, connect to battery, ground it. Right, now label this resistor as RS, this as RD, this as RG. Right, this battery as E. Then mark current flows. Two things: mark current flows and potential differences. Then we know direction of current here is downwards, IS. This is downwards, ID. Right? No current flows in the gate terminal. This potential difference is called VGS. This potential difference is called VDS. This is called VDG. Right. Anyway, check your diagrams. Check your diagrams. Oh, this part is not visible. See. Right. And check it further again. Check it further again. Right. So as we had VCC here in a bipolar transistor, VCC in a bipolar transistor, here we have VDD. Label this as VDD. This point up. Label this point as VDD. VDD. Right. Label that point as VDD. Right. Listen now. Listen. Listen carefully. The core part, core area. Listen. In a bipolar transistor, we have two special things, two unique things that we did about a bipolar transistor. One is writing straight line, the other one is writing the cross line. Cross line and straight line, writing cross line and straight line were two special things, specific things about a bipolar transistor. When it comes to unipolar transistor, right, there are no such things. No special things. There are no such things. Right? All unipolar transistor questions are solved by using delta V equals IR. Right? All the questions are solved by using delta V equals IR. Right. Now I will guide you for something because we are going to prove an equation first. Right? To prove that equation, first I will guide you. I will guide you through. Right? Then follow my instructions and prove the equation. Then I will do the proof. Right. First thing is apply delta V equals IR. Apply delta V equals IR for RD. Apply delta V equals IR for RD. First thing. Apply delta V equals IR for RD. Apply delta V equals IR for RD. Delta V equals IR for RD. Apply delta V equals IR for RD. Right. Now let us simplify. Keep that equation there. Keep that equation there. Right. Then apply delta V equals IR for RS. Then apply delta V equals IR for RS. Apply delta V equals IR for RS then. Delta V equals IR for RS. Delta V equals IR for RS. Use these notations about IS, VS, VG, VDG. Connect use one. Right, for RS. Right. Then find VGS. Find VGS. Use your knowledge on, right? Find VGS. Use your knowledge on what? Electricity. Use your knowledge on electricity and find VGS. VGS is the potential difference between gate and source. VGS, potential difference between gate and source. VGS. Right. And then tell me what's the final answer you got for this? I need the final answer for VGS. What's the final answer you got for VGS? That's what we need. What is the topic about this? Applications of NJFET. Applications of NJFET. Right. What about VGS? Anyone? What about VGS? Anyone? What do we have got for VGS? Oh, right. Check your working sound for RD. For RD. RD is here. Right? For RD. Current flows from this terminal to this end to here. Then potential difference is we are using delta V equals IR. Delta V equals IR. Then potential difference across RD is VDD minus VD. VDD minus VD equals ID RD. Keep it there. Right? Keep it there. Then for RS. For RS. Potential difference between RS is current flows from S to 0. Then PS minus 0 using delta V equals IR. We are using delta V equals IR. Then delta V is PS minus 0. Vs minus 0 equals what's the current IS? IS RS. Then this is Vs equals, this says Vs equals IS RS. Right? Current stable, this has equation 1 and this has equation 2. 1 and 2. Right, now we need VGS. VGS, potential difference between G and S. No? How can we expand VGS? Electricity. VGS is expanded as VG minus VS. VGS is expanded as VG minus VS. Then VGS equals VG. What about VG? There's no current flow here. There's no current flow here. And the reason to connect that RG is, right? There's no current flow. There's no current flow. The reason to connect that RG is, even if given a small current flow tries to come through, right? To omit that current, the resistor is connected for the safety, right? For the safety. And usually that RG is connected in a very high value like mega ohms. RG is usually connected in a very high value like mega ohms because always we have to keep IG 0, right? To keep IG 0, right? To make sure a very high resistor is connected. Alright. Okay, then we know VG equals 0. If this is 0, no current here, VG equals 0. No current flows here, no current flows, VG equals 0. Then here we know, since VG equals 0, since VG equals 0, make it 0, then 0 minus Vs, right? Then VGS equals minus Vs, Vs is ISRS, right? Vs is ISRS from equation 2, right? Again we know, in a unipolar transistor, always Is equals ID. In a unipolar transistor, always Is equals ID. Right? Then if I replace this Is with ID, right, it says VGS equals minus IDRS. Minus IDRS. Right? This is how we usually refer this equation. This is how we usually refer this equation. And at once we can use this as a proof regard. VGS equals minus IDRS. VGS equals minus IDRS, and this is the general equation of a unipolar transistor or a NJFET. Right? This is the general equation of a NJFET. Right? Now, equation is for VGS. No? This transistor, this instrument, this appliance is going to control using VGS. Right? That's why it was called a voltage control device. Right? This is controlled using VGS. This is controlled using VGS. Right? That's why it's called a voltage control device. In the references, that's why we discussed that as a voltage control device. Right? Check your workings and make if any changes. Right? Then after this, we'll introduce these terms also. Right? Introduce these terms also. VGS, ID, RS. Introduce the terms also. And I'll ask if any questions also. Right. Okay. Uh, Identify these terms of no EGS. What is EGS? Write down potential difference between gate and source. EGS. Identify. Potential difference between gate and source. 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 Right? Then ID drain current. ID drain current. Drain current. ID drain current. ID drain current. Then RS source resistor. 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 Source resistor. RS source resistor. Right. Then write down below with the red pen. Write down below with the red pen. Mention below with the red pen. Right. Mention below with the red pen. With the red pen. This equation is valid. This equation is valid. This equation is valid. This equation is valid. For any NJ FET. This equation is valid 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 for any NJ FET except voltage divider circuit. This equation is valid for any NJ FET except voltage divider circuit. Right? Except voltage divider circuit. Right, now let's see a real application with numbers. Let's see a real application with numbers. Go to page number 22. Page number 22. Practice question 1. Go to page number 22, practice question 1. Go to page number 22, practice question 1. Any questions? How to identify source and drain? With respect to direction of current flow only. With respect to direction of current flow only. Right? Can we switch? Yeah, can switch. Can switch. Can switch up and down. Not only up and down, right? Can be oriented in any kind of direction. Just as a bipolar transistor. Right? Can be in any kind of an orientation. And it's yes. Page 22, question 1. Go to page 22, question 1. Right. And take down circuit and identify terminals, mark currents and potential differences. Mark those things. We need to get the start. Mark those things. We need to get the start. Right. Mark those things. We will need to get the start. Right. This is given. Question 1. $400 ohms. This is RS, 400 ohms. Then 5 mega ohms is connected and it is grounded somewhere here. 5 mega ohms. Then RD 2 kilo ohms. 2 kilo ohms. Battery and the grounding. Right, two batteries. VDD is given as 30. VDD is given as 30. Right. So you know this is gate, drain, and the source. Right. Now let's see the first one. And the current is given 4 milliamperes. Sorry, current is given 4 milliamperes. And you better mark this current along the circuit like this. Mark the current as 4 milliamperes. 4 milliamperes. Current is given 4 milliamperes. Right. Now see first one, VD. First one, VD. Questions are very easy because as I told you, there are no any specific things we do. Right? All the questions are given. All the questions are done just by using delta V equals IR. That's it. That's the convenience we have behind this. That's the convenience we have behind this. Right. Then first one, to find VD, what you can do? Apply delta V equals IR for RD. For RD. Apply delta V equals IR for RD and find it quickly and tell me answers. And tell me the answers. That's it. Right. Very easy to score when it comes to these questions. Very easy to score. Usually this comes as a part for 10 marks or 15 marks in the essay paper. 10 to 15. 10 to 15 here. Right? Easily score on good. And in my practice questions, I have asked all possible things to be asked. But when it comes to exam questions, right? Like 2-3 things from this five will be asked. Right? Since we are practicing, I have given all the possibilities. Right? Otherwise, when it comes to an exam question, like 2-3 things, right? Starting with the theory part usually, right? Starting with the theory part usually, and then like 2 calculations or maximum 3 when like 2 calculations will be asked. in covers like 15 marks. Can cover up to 15 marks. Right, what about VD? First one VD. Very straightforward VD. Then for Arduino, then VDD minus VD. First, write this equation this way before you substitute values. Then VDD minus VD equals ID Arduino. ID RD. This 4 milliamperes flows through this, which means ID is actually 4 milliamperes. VDD is given 30. Then 30 minus VD equals ID 4 milliamperes, 4 times 10 to the power minus 3. RD 2 kilo ohms, 2 times 10 to the power 3. These two cancels off. 8, which means VD equals 22 volts. 22 volts. Right? Then part 2. Part 2. VS. VS. To find VS, see, very straightforward. To find VS, apply delta V equals IR for RS. For RS. Delta V equals IR. Right? Then this is our ID. This is IS. Right? We know that always IS equals ID. We know that always IS equals ID. IS equals ID. Right? Then no problem. IS equals ID. Delta V is VS minus 0. Right? First, writing labels VS minus 0 equals IS RS. IS RS. Plug values. We need VS. IS equals ID. No? ID is 4. Then 4 times 10 to the power minus 3. RS 200. Right? Then only 10 to the power minus 1 remains, which means 1.6 volts. 1.6 volts. Right? 3 VGS. Right? Either you can use that root equation or since VS is known, use VG minus VS. Either way, you will get the same. Then VGS. VGS is VG minus VS. VGS equals VG0 because always G of minus VS 1.6. Then VGS equals minus 1.6 volts. And here you have to mention this that VG equals 0. VG equals 0. Right? 4. VDS. There are no equations for VDS anyway. Then use your electricity knowledge. VDS is VD minus VS. VD was known. VD here 22. VS is here 1.6. Then 20.4. 20.4 volts. Then 5. VDG. Same thing. VDG. VDG is VD minus VG. VD minus VG. Right? VD was 22. VG 0. Right? VG is 0. G of. Right? Then VDG is also 22 volts. VDG is also. Right? So likewise, there's nothing unique or specific about this. Right? Simply what we do is applying delta V equals IR and finding everything out. Right? Applying delta V equals IR and finding everything out. Raise your hand if this is clear. Raise your hand if this first calculation is clear. Right. Okay, clear? Write down. If any changes, write down if any changes. Write down if any changes. Okay, finished? Another. Finished? No questions. Fine. Mega है ना lazy वाला easily you can score, right? So actually speaking, these questions are very easy. These questions are very easy. Fine. Then go to question two. Go to question two. Very much the same type. Go to question two. Start trying. Start trying. Start question two. Start question two. Start question two. I will also start in 3 minutes. Very easy. I will start in 3 minutes. You can start question two. Fine, question two. Yeah, I can see some answers. We are receiving answers. Good. Good, good. ID 6 times 10 to the minus 3. Question 2. Right. Two kilo ohms, 400 ohms, rounding, then RG 6 mega ohms, VDD is given 20 volts. VDD is given 20 volts. On C. Once again. Give me 1 second. So adjust the camera. Right now it's zero. Right, VDD 20 volts, VDD 20 volts, then 2 kilo ohms, 6 mega ohms, and VD is given 8 volts. VD is given now. VD is given now 8 volts. VD is given. So we know this is our gate, drain, and source. Mark current flows. IS, ID. Potential differences, VGS, VDS, VDG. Right. So before you start, mark everything that you need in the calculation and start. Mark everything that you need in the calculation first, right? Before you start, and then start. And then start. Okay, right. What's the first one? ID. ID. Now VDD and VD are unknown. Then to find ID, apply it because they are for 2 kilo ohms. Very straightforward. First one. Then 4. 2 kilo ohms. 2 kilo ohms here again. That is RD. So RD. Delta V equals IR. Then VDD minus VD equals IDRD. VDD is 20. Right? VD 8 equals ID. RD is 2 kilo ohms. 2 times 10 to the power 3. Simplify. 20 minus 8. 20 minus 8. 12. 12 equals ID times 2 times 10 to the power 3. Then ID equals 12 over 2, 6. Then 6 milliamperes. 6 milliamperes. 6 times 10 to the minus 3. 6 milliamperes. Right, then second one. Second, Vs. Vs. To find Vs, apply for Rs. Delta V equals IR. Vs minus 0 equals IS Rs. Then Vs equals, you have to mention that Is equals ID. Right? They are logics. Mention that Is equals ID. Mention that Is equals ID. Then Is equals ID. ID is 6 milliamperes, 6 times 10 to the minus 3. Rs is 400. 400. Then Vs equals 2.4 volts. 2.4 volts. Right? Number 3. Number 3. VGD. VGD. VGD is written as VG minus VD. Right? VGD is written as VG minus VD. VGD is us, right? Yeah. VGD is written as VG minus VD. Then VGD equals VG0. Right? Have to mention that G of, right? VG equals 0. G of minus VD. VD was given 8. Then VGD is minus 8. 4. 4. VDS. 4 VDS. VDS is VD minus VS. Right? VD is 8. Minus VS. VS is 2.4. That is 5.6. Right? Now in this one, VGS is not task. Right? If you find VGS also, VGS is VG minus VS. Right? Or else you can apply minus IDR as omega. VG is 0 minus VS 2.4 minus 2.4 volts. Right? That's it. Check it to answers. Check it to answers. Right? VGD minus 8. Correct. Minus 8. Correct. Good. VGS minus 24. Sorry, VS 2.4. Correct. Okay, right. Any questions so far? Any questions so far? Any questions so far? Or is it all clear enough? Any questions or is it all clear enough? Clear. Right. Then let's move on to the next part. Let's move on to the next part. Right. Next heading. Write down voltage divider circuit. Next heading. Voltage divider circuit. Voltage divider circuit. For NJFET. Voltage divider circuit for NJFET. Voltage divider circuit for NJFET. Voltage divider circuit for NJFET. Right. So you have to do what I say again. Draw NJFET at the center. Right. Keep some space above also. Right. Keep some space above also. Around the middle of the page, draw a NJFET. Around the Middle of the page, draw NJ FET. Draw NJ FET. Draw NJ FET around the middle of the page. Right? Identify terminals. Identify terminals. Identify terminals. Extend source and connector resistor. Extend source and connector resistor. Ground it. Label the resistor as RS. Extend drain and connector resistor. Label it as RD. Extend gate backwards and connect two resistors like this. Connect two resistors like this. Label this as VDD. Label these two resistors as R1 and R2. Gate, drain, source. Right? Listen now. Now always when you learn voltage divider here in the unipolar transistors, voltage divider in the FET, in JFET, right, or in JFET, compare this with voltage divider circuit we had for bipolar transistor. Compare this with what we had for bipolar transistor. Right? Very comparative. Very comparative. Right? Circuits are the same thing. Same thing in the bipolar transistor circuit. That bipolar transistor is replaced by the unipolar transistor. That's the only difference. Right? Now, what happens is this. Listen. Now what happens is this. We know if this is VDD, right? This is also VDD, same wire. Up to here, that is VDD. Right. Now, the thing is, we know there are no current flows through gate. There are no current flows through gate in a JFET. Right? There are no current flows through gate in a JFET. Then first mark our known currents. This is our ID. This is our IS, known currents. And about here, say this current here is simple line. What happens is, for the simple line which comes to here, right? It can't go into the gate because there are no current flows. There are no current inflows to the gate. Right? Then, without dividing, this total current flows down like this. This total current flows down like this. Right? Which means, now this is the point, which means same current flows through R1 and R2. Same current flows through R1 and R2. If same current flows through both resistors, these two resistors are in series combination. Since these two are in series combination, we can apply voltage divider to find VG. If this is G, this point is VG, no? And if that is G, this point is VG, no? Now we can apply voltage divider to find VG. Right? That's why this is called the voltage divider circuit. Very much same to the idea we had in bipolar transistor. Right? Complete this, mark currents and complete this. See how comparative. Same thing. Same thing. Right? Okay. Right on below. Right on below. Right on below. Right down. Same current flows through. Right down below. Same current flows through R1 and R2. 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 Hence, they are in a series combination. Hence, they are in. Hence, they are in a series combination. 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 Right. Next line, right again. By using voltage divider for R2. Right down. By using voltage divider for R2. 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 Voltage divider for R2. Right. Apply now. Apply and find VG. Apply and find VG and tell me. Apply voltage divider and find VG. For R2, potential difference across R2, VG minus 0. Total potential difference of the system, VGD minus 0. Over addition of resistors R1 plus R2. Right, we need this across R2 into R2. Right, then VG equals VDD R2 over R1 plus R2. Right, this is VG. This is VG. Now the thing is, you can clearly see VG is non-zero. Initially means in all other applications we had VG was 0, G off. But now G is not off, VG is non-zero. Since VG is non-zero, now this is where the other thing comes. Since VG is non-zero, now our equation, proved equation, VGS equals minus IDRS cannot be used. Because when we were proving VGS equals minus IDRS, we considered as G off. Now it cannot be used, right? So that's what I meant before by the equation cannot be applied. The equation cannot be applied for voltage divider, right? That's why it cannot be applied, right? First, take up to here, right up to here. Okay. Then write down below with the red pen. Below with the red pen, put an asterisk mark and write down with the red pen. With the red pen, write down. Therefore, VG not equals 0 in voltage divider circuit. Therefore, VG not equals 0 in voltage divider circuit. 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 Next point, keep using red. Next point, keep using red. So that VGS equals minus IDRS cannot be used. So that VGS equals minus IDRS cannot be used. So that VGS equals minus IDRS cannot be used. Right? It is not that. Cannot be used. Right? So that's it. Other than that, applying the equal IR is always possible for any resistor, right? Then other than this, applying the equal IR can be done. Like dimension card Right, write down furthermore, furthermore, right? Applying delta V equals IR or V equals IR is totally possible for all four resistors, right? For all four resistors. Say for RD first, for RD if you use VDD minus VD, VDD minus VD, very much same as before, IDRB, right? For RS if you use, for RS, VS minus 0, VS minus 0 equals ISRS. Then for R1 if needed, for R1 if needed, then potential difference VDD minus VG, VDD minus VG equals simple lie R1. Then for R2, if needed, VG minus 0 equals I R2. So likewise, this is always possible. That is delta equal to IR, valid for any resistor. Right? About voltage divider, only this thing is adding up. Right? Take down. We'll do a question. Take down. Right. Go to question 3. Go to question 3. And after this, go to question 3. Page number 22. Question 3, page 22. Go to question 3. And start it. Go to question 3 and start. Question 3. Start question 3. I will start after 3 minutes. Start question 3. Start question 3. Right. Right. Start. Are the answers? Are the answers? Right. Any answers? VG 6 volts. VG 6 volts. Right. Question 3. Two kilo ohms. 6 kilo ohms. VDD given 20 volt. VDD 24 volts. 4 kilo ohms. VD is given. VD is given 16 volts. Right. 5 kilo ohms here. Right. A voltage divider circuit of an JFET is given. Determine the followings. Determine the followings. It should be connected as determine the followings. Determine the followings of if VD is given as 16. Okay. VD is 16. Determine followings. Now mark currents, identify terminals. Right. Gate. Drain. Source. Our usual currents. This is ID. This is IS. And if this is VDD up to here, that is VDD, right? Then the current flow here, that is same, right? First question, VG, right? First question, VG. Then when finding VG, we are using that R1 and R2, 6 and 2, 6 and 2. Series, no, you have to mention it because that is series, because of this IG. IG is 0. That's a special case, otherwise there is not just a series connection with a single connection. Right? Even though it has a junction, it is still series because there is no current flows through gate. That we have to mention always. Then mention the logic. 6 kilo ohms and 2 kilo ohms. 6 kilo ohms and 2 kilo ohms are in series combination. Series combination. 6 kilo ohms and 2 kilo ohms series combination. Series combination. Right? And mention within brackets. IG equals 0. Mention within brackets. IG equals 0. Right? Then you can say this. Using voltage divider for 2 kilo ohms. You can use it for any resistor. Using for 2 kilo ohms is easier because that is grounded. That is grounded. Right? Grounding is zero. Right? Grounding is at zero voltage. Right? If there is zero, this is also zero, same wire. Then apply total VDD minus zero. And sorry, potential across this VG minus zero equals total VDD minus zero over addition 6 plus 2 into 2. Right? Plug values and simplify. VG equals total 24 over addition 6 plus 2, 8 into 2. Right? 3, then 6 volts. VG equals 6 volts. VG equals 6 is correct. VG equals 6 volts. VG equals 6 volts. Right? Then ID. ID, what about ID? This is number 1. First calculation. Second one, ID. To find ID, apply because I have 4 kilo ohms. 4 kilo ohms for RD. Delta V equals IR. V equals IR. Right? VDD minus VD. VDD minus VD equals ID RD. Right? Then 24 minus 16. 24 minus 16 equals, we need ID. Right? RD is 4 kilo ohms. 4 10 to the power 3. This is 8. 8 equals ID. 4 times 10 to the power 3. Then ID equals 2 milliamperes. ID equals 2 milliamperes. 2 times 10 to the minus 3, correct? Not 2000. 2 times 10 to the minus 3. 2 milliamperes. 2 milliamperes. Right? Then IS. IS. Nothing to find about IS because IS equals ID. IS equals ID. Then IS equals 2 milliamperes. VS. To find VS, apply delta V equals IR. 4 RS. 4 RS. Delta V equals IR. 4 RS. Delta V equals IR for RS. Delta V equals IR for RS. Delta V. Delta V. VS minus 0. VS minus 0. IS RS. We need VS. Right? We need VS. IS is 2 milliamperes. 2 times 10 to the minus 3. RS is 5 kilo ohms. 5 times 10 to the power 3. Cancel it off. Then VS equals 10 volts. 5. 5. VGS. Now equation can be used. VGS is VG minus VS. Right? VGS is VG minus VS. VG is 6. VS is 10. Then minus 4. Minus 4. And then VDS 6. VDS. Again, same thing. VDS is VD minus VS. VD minus VS. Right? VD minus VS. VD. VD was 16. VS 10. 6 volts. Right? So likewise, that calculation goes. Right? And the good news is there are only 2 types of calculations you are getting from NJFET. Right? First type is the normal application. Second type, voltage divider. Only these 2 types. Right? Very easy to handle. Only these 2 types. Bipolar types for FET. In bipolar, we have the normal one, common emitter configuration, normal, and then voltage divider, then working as a bridge, right? Functioning as a bridge, and region wise calculations, right? Different things are there. Here, nothing. Right? Check if any changes. Check if any changes. Right. Right. Any questions so far? Any questions so far? Anything? Raise your hand if everything is clear up to this point. Raise your hand if everything is clear up to this point. Or ask if any questions. Clear? Right? That kind of bipolar again, make analyze here. When it comes to questions, very easy to score. Very easy to score. Right? Bipolar lazy, but this is even easier. Bipolar lazy, right? I don't say it's difficult, it's also easy, but this is even easier. Right, then I will move on. Next heading. Next heading, write down. Output characteristics, write down. Output characteristics. Output characteristics curve. Output characteristics curve of NJFET. 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 Right, listen. Right. So when it comes to characteristic curves, we have three characteristic curves in bipolar. Remember, we had three characteristic curves for a bipolar transistor. Right, input characteristics, then current transfer characteristics, and output characteristics. But when it comes to here, right, unipolar transistor, or rather FET, there's only one characteristic curve we draw, right? There's only one characteristic curve we draw. We don't draw input also because this is in a reverse bias state, no? Not a forward bias, that's a reverse bias state. So we don't draw any input even, and there's nothing called current transfer. So only characteristic curve we draw here is output characteristics. Right? Now I will compare this with the NPN because NPN and JBET is always comparative, no? First, let's see, this is the output characteristics. Let's see the output characteristics of NPN. So if you can remember, plot the graph, plot the curve, if you can remember. This is for NPN. For NPN, it is not between IC and VCE, right? IC and VCE, IC and VCE. And the curve was like this. And the curve was like this. So usually we got like three curves and regions were identified. And when this graph is plot, IV is kept at constant values, right? Now recall the things you learned before. Right, IV is kept constant values, kept at constant values, say 50 microamperes, 100 microamperes, 200 microamperes, right? And then we label regions. We label all regions. Right, this region where IC is close to 0 is cutoff region. And where VC is close to 0, this is saturated region, right? This side, saturated. Let me label here. Saturated region. And here, there is active region, right? This shows the output characteristics of a bipolar, right? Output characteristics of a bipolar. That was the output of a bipolar, output characteristics of a bipolar. Now, going to compare this with output characteristics of this unipolar NJFET, right? This is for NPN, and this is for NJFET, right? You better take down both because always when you study this also, you'll be able to compare. This is for NJ right? Should be able to compare. Then take down both when you take down both. Right. Listen. Now instead of IC, here we have ID. No? Instead of E, we have S, then VCE should be VDS. VC should be PDS accordingly. Right? Now, this is like this. Listen. Listen. This is like this. This has a kind of a unique shape. Right? This part is linear and then deviates. Then go into some breakdown region, deviates like this. And from the same curve, these ones are also deviated like this. Right? Like this. And here, listen. As IB is kept constant in a bipolar, right? In this one, VGS is kept constant, right? Because our controller is VGS. Our controller is VGS. This is voltage control. Our control is on VGS. Then VGS is kept constant. These are 4 different lines. 4 different lines. Then here, say VGS equals VGS is always minus, because minus IDRS, no? VGS is always minus. VGS is minus IDRS. Voltage divider this is the normal usage. Voltage divider is a special circuit, no? VGS, say this is a minus 4 volts, minus 3 volts, minus 2 volts, minus 1 likewise. It's there. And here, regions are also there. Here, regions are also there. Right, listen. This region where it behaves linear. This region where it behaves linear. ID and BD is a linear curve, goes through center, goes to origin. Center, sorry, origin. Right, that's a straight line, goes to origin. No? So which means it follows Ohm's law. Therefore, it is called ohmic region. Therefore, it is called ohmic region. Right, V equals IR, OV proportional to I, ohmic region. And here, this part, it works steadily. It works steadily, right? It works steadily. Is called saturated region. And after that, here what's happened is it's going to burn out. Burning out means, listen, burning out means that's a reverse bias PN junction. No? That's a reverse bias PN junction. When voltage is increased, voltage difference of the PN junction is increased further and further and further. We know it reaches a reverse breakdown voltage, right? PN junctions, right? They are in color. PN junctions. It reaches a reverse breakdown voltage, then it breaks down, right? So therefore, it's called the breakdown region. And this is the breakdown region. Breakdown region, right? So likewise, should be able to compare, and you have to memorize both of them. Should be able to compare as well, right? Take down. This is sometimes called the pinch off region also. In brackets, pinch off. Pinch off is coming next. Pinch off region. Pinch off region. Pinch off. Take down. Right, last 5 weeks, right, like 35 days from the exam, 35 or 36. So again, last 5 weeks and 1 day. 5 weeks and 1 day. 5 weeks and 1 day from the exam. Right. I'm just staying aside for you to finish theory. Right. Take down. It's the same thing we know from the previous learnings. Right. Compare this with the output characteristics of the NJFET, NPN to NJFET. Right. NPN to NJFET. Right. All right. Finished. Finished. Shall we move on? Okay. Let's move on. The last heading here in FETs. Last heading here in FETs. Write down pinch of voltage. Write down pinch of voltage of a unipolar transistor. 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 Within brackets VB. Within brackets VB. Pinch of voltage of a unipolar transistor VB. Pinch of voltage of a unipolar transistor VB. Right. So then what is pinching? Pinch. What is pinch? Pinching, pinch. Pinch off. What's the meaning? Pinch. Pinch means it's like annoying someone with fingers. That is called pinching. Right? That is called pinching. Annoying someone with fingers. Ponittanawa කියලා කියන්නේ. Ponittanawa කියන්නේ pinch. Ponittanawa කියලා කියන්නේ pinch. Right? Now this is pinch of voltage. Right? And this name comes for a reason. Right? You will see the reason here after the explanation. Right? Listen. Now we know in our unipolar transistor NJFET, in our NJFET, now when current flows, this is what happens. See? Now if this is the NJFET, if this is the NJFET, right? So this is N, body is N, body is N, and these sides are P. This is the N channel, NGFN, right? And terminals are drain, source, and the gate, right? Now, what happens is when this operates, current flows from D to S. When this operates, current flows from D to S. Then current flows from D to S. ID, right? IS, current flows from D to S. ID and IS, right? We know, since this PN junction is in a reverse bias state, right? This current is a leakage current. There is a considerable current, but there is a leakage current. PN junction is in the reverse bias state. There is a leakage current. That is reverse biased. Since the PN junction is reverse biased, we know there's a depletion region here. Anyway, there's a depletion region, and especially when the PN junction is reverse biased, depletion region gets broader, right? PN junctions, right? Recall it from PN junctions. When the PN junction is in reverse bias state, depletion region increases. It's getting wider, getting broader. It develops. Now, when current flows, right? Already there's a depletion region here created. Because of the PN junction, like this. There's a depletion region, right? And when current flows downwards, flow of electrons is upwards. So let me mark the flow of electrons also like this. See, when current flows downwards, flow of electrons is upwards. Right now, what happens is when we change the voltage between, when you change the voltage between DNS, what happens is this voltage difference between, right? PN junction changes. When voltage difference between PN junction changes, right? That's in a reverse bias state. That reverse biasness increases. When reverse biasness increases, depletion region grows. Depletion region increases. Right? Then, when this potential difference is increases, depletion region gets increased like this. It gets increased. Likewise, if you keep on increasing this voltage, this increases, keep on increasing like this. And it will be reaching a point where depletion regions from both sides are combined together, are merged together. It's reaching a point where depletion regions from both sides are combined together. At that point, we know in the depletion region, we know there are only static charges, right? There are only static charges in the depletion region. Then when these two are in contact, there's no chance for these electrons to flow. Then at that point, the flow of electrons stops. Then no current flows in the circuit. Right? Since electrons are stopped by pinching by this depletion region, this is called the pinch off voltage. Right? Electrons are like this depletion region is disturbing electrons. Right? Annoying electrons. That's why it's called the pinch off voltage. Right? So at the pinch off voltage, no current flows. And voltage difference between D and S, right? At this point is called pinch off voltage, PV. Right? And this pinch off voltage is comparative to cutoff voltage in bipolar. Cutoff in bipolar, no currents. Right? Pinch off in unipolar, no currents. Right? Take down the diagram. And you better label depletion region. Take down the diagram. Take down the diagram. Right, take out. Right, finished. Does it region combine a pinch of voltage? Exactly. Yes. It merges from both sides, combines from both sides, and stops the flow of electrons. And stops the flow of electrons. Right? Okay, finish. Finish. Write down in point form. First point. Write down in point form. Write down in point form. First point. First point. PN junction of. Write down. PN junction of. PN junction of. PN junction of. Any JFET is. PN junction of any JFET is. PN junction of any JFET is always reverse biased. PN junction of any JFET is always reverse biased. Next point. Next point. When current flows from. When current flows from. When current flows from. When current flows from D to S. When current flows from D to S. D to S. Respective electrons. Respective electrons flow from S to D. 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 Next point. Next point. When current keeps flowing. 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 Depletion region keeps. Depletion region keeps developing. When current keeps flowing, depletion region keeps developing. When current keeps flowing, depletion region keeps developing. Depletion region keeps developing. Since PN junction is since PN junction is at reverse bias state. 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 Reverse bias state. Right. Next point. Next point. When depletion regions from both sides. 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 Both sides are merged together. Are merged together. Are merged together. Are merged together. Flow of electrons stop. Flow of electrons stop. Flow of electrons stops. Flow of electrons stops. Flow of electrons stops. Next point. Potential difference between potential difference between potential difference between DNS. Potential difference between DNS. Potential difference between DNS. Drain and source DNS. Potential difference between DNS. At this point of NJ 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 is called at this point of NJ is called pinch off voltage. At this point of NJ is called pinch off voltage. At this point of NJ is called pinch off voltage. At this point of NJ is called pinch off voltage. At this point of NJ is called pinch off voltage. Right. Next point, user and pen. Next point, user and pen. Cutoff voltage in bipolar. Cutoff voltage in bipolar. Cutoff voltage in bipolar. Cutoff voltage in bipolar. Cutoff voltage in bipolar is comparative to pinch off voltage is comparative to pinch off voltage in unipolar. Comparative to pinch off voltage in unipolar transistors, right? Is comparative to pinch off voltage in unipolar transistors, right? So with that, we have come to the 100% completion of unipolar transistors, right? And transistors. Any questions before we jump into the next? Any questions? Easy, 100% completion of unipolar transistors, FETs, right? And with that, this is the completion of all transistor parts. Any questions? So how the depletion region forms? Day one of analog, right? Day one of analog, PN junctions. Is it clear enough? Raise your hand if clear enough and ask if any questions. All right, then that's the end of unipolar also. Right. The next thing we are going to start now is op amps, operational amplifiers. Next thing we are going to start now is operational amplifiers. Right. I need to take a small break of like 5 minutes. Now the time is exact time is 38. Right? Let's have a break of just 5 minutes and come back. Right? I'm going to start op-amps after the break. Right? Get a small break. 5 minutes again, 5 minutes, 5 minutes again. 5 to 7. A small break. (9:30) leave now. We'll be back at 9:45. Right, if you are fetching yourself, just refresh and come back.